Good morning, everybody. It's my pleasure to be here, and I'd like to thank Yunus and Morgan both for extending this invitation. I wouldn't have missed it. I just started working in the area for the past year and a half, 2 years now. Mostly a pulse sequence designer. I'll talk to you a little bit about what that is. One of the goals in my laboratory is to make sure that some of these tools are easily and readily available and accessible. So my laboratory at Mount Sinai is called the Accessible MRI Laboratory. I'm going to talk to you about how you can make pulse sequences accessible, and all you need is an internet browser. So you don't need to install anything and you can get started with just that. With that, please feel free to stop me at any point if you have any questions. I'm more than happy to take them as we go along. I have about 50 slides for an hour, but I can cut them through as and when you like. My lab receives research funding from a bunch of places. With that said, I'll talk to you about why we need pulse sequence programming, and I'll introduce you to what is pulse sequence programming just a little bit, and tell you why we need to move in the direction of open source, vendor agnostic pulse sequence programming. Mention to you the tool that we've been developing for a while, about the last 7-8 years, on making pulse sequence programming available to everybody. And then I was hoping for a demo. If there is internet, I'm happy to do it now, or in the afternoon, whenever we can get around. I have a file that I can share, which will be your first pulse sequence, and you can program the scanner. Also talk to you about virtual scanning. If you wanted to go back to the lab and you don't have access to the MR system to play with, if you wanted to do this on software, play a few games, kind of equip yourself with the first few steps to do that. Then I'll summarize. Before getting into open source pulse sequence programming, let me tell you what it is about. So once you put the hardware together, I'm guessing some of that has been spoken about yesterday. I saw Tom up on stage, so I'm thinking you have spoken about is NDFEB magnets and how you make the magnet array and the 3 coils. If not, I can take a step back and say the MR scanner hardware has 3 kinds of coils, and they all produce different kinds of magnetic fields. But then it's a very carefully choreographed dance, and the dance happens via the laptop. And you basically tell which magnetic field is to get produced. For that, you move these pulses. And this whole choreography of playing pulses on one of the 3 coils, usually 2 out of the 3 coils, is called pulse sequence programming. By doing this, you can look at different kind of contrasts, meaning if you're after a particular part of the anatomy, you want that to get highlighted. For example, if you wanted to look at black versus white, white versus black, gray, then you probably tinker and tailor a little bit of how these pulses would be played. When you do this, then you can actually start kind of, instead of using a car as it is, you can actually start thinking whether you can use that car more efficiently. Can you make that car behave like a sports car or a sports truck or a heavy weightlifting monster truck? That is all dependent on pulse sequence programming. How efficiently you do that. For that, I've listed about 3 specific uses. At low field specifically, you can't be scanning somebody for 40-45 minutes. So if you know these tools of what I'm going to show, you can probably scan faster. You can improve signal to noise ratio if you did some of the tricks using pulse sequence programming. On a typical vendor, call them the GPS system, for lack of a better phrase. GPS stands for GE, Philips, Siemens, not necessarily global positioning system in our case. You need to know what is the vendor specific programming environment. Meaning, if you have to program a G scanner, you need to know Epic. If you're programming a Siemens scanner, you need to know a platform called IDEA. Just learning this tool takes about a few years before you get to do something. So the idea then is, can we make certain tools available to you, just like how machine learning tools are available in the realm of MR and pulse sequencing. There are a whole bunch of tools out there which let you do different parts of this MR pipeline. I won't bore you with the slide, but I just want to give you a sense of the number of choices you have available to you, which is openware and open source. And as you go from left to right, there are different things that you can do with it, starting from simulations, acquisitions, reconstructions, and the like. So here is a more recent outline that my colleague Maxim and his colleagues have put out, which is, if you were to do all of this open source here, right? You're looking at the hardware, you're building the hardware. Now you think you want to also have the software open source. This is one configuration to put it in. You would use PyPulseq, which is the tool that we've been building, but Maxim's been working on PulseSec. And then you have a bunch of UI options called 5M. I'm going to show you another one. And then you have something called as the ISMRM, International Society for Magnetic Resonance in Medicine. They have their own data format, and then you have a reconstruction tool. So all of this is open source. This is one example. You can put in a bunch of these pipelines together. But the focus of my talk today is, if your hardware is ready and then you feel like programming it on your own, what are the options you have to do that? So the next level dive on that is to look at the architecture. Again, this is from Bedman this year related, talking about how you want to put stuff on a personal computer. I don't know why they're stuck to showing the old PC, it could be a laptop. And then the lead pitaya, which I think the console you might be using right now might be a Kia spectrometer here. But there is another one called SDR Lab from Red Pitaya, which is much cheaper and easier to program, and that's available too. Talk to you about what we can do for Python. Is there anybody in the audience here interested in programming or has any kind of Python programming experience or interest? That's good. That's good. I see a bunch of hands. So that's awesome. So in MRI, there are tools using Python for simulating MRI. Like, I want to work on a few experiments, figure out, and then come and play whatever I've developed in-house. So that's called simulations. So you have a tool called graphical programming interface using Python. Then once you get the data from the scanner, you need to reconstruct it. Oftentimes, the most robust analytical tool is the Fourier transform. But with recent advances in deep learning, which I'm going to show you tomorrow, you can do a bunch of other things as well. But you have a library for that too. This part probably some or most of you recognize, which is, you have SciPy, LibCV, NumPy, Scikit-Lab, and so on and so forth, for visualizing these libraries, to visualizing these data, also looking at image processing and the like. This mostly is everybody's go-to tool now. Could be PyTorch, TensorFlow, Keras. That's what you have for deep learning. The missing part to this whole story was MR acquisition. So if you're going to acquire data in an open source way, probably downstream stuff is going to be challenging. So that's the focus of what I'm going to be talking today, and my lab has been working for a few years now. So it kind of integrates this whole pipeline when we also include MR acquisition. Is the process of getting data from the scanner. Won't bore you with the details, and I'm happy to go into details offline. But the key idea that I want to present is if you're sending pulses to the scanner, saying turn on coil 1, RF coil for example, turn on coil 2, gradient coil for example, and then turn off the receive coil, which is my ADC. How many of you have a background in electrical engineering or the like? Anybody here with electrical engineering? Okay, just one. So I'm just going to quickly talk to you about what happens on an MR system for the rest of you. Once we turn on the magnet, it produces a magnetic field. Right now we are actually in a big giant magnetic field called the Earth. So people do MRI using this planet as well. Called N62 story. It's called Earth Field NMR and MRI. You can build one for $200 US. And there's a paper on it by Carl Mikal from University of British Columbia. True story. So we are actually in a big magnet right now, and the protons in your body are either aligned to or opposite to the north pole of the Earth's magnet. So when we want to do it at a higher magnetic field, you build this kind of system that you're building, and then you say, I want to actually move it away from its alignment and then watch it go back. That's the whole process that we're looking at. For that, you need to send out a pulse, just like you send out a pulse from the radio station tower to your radios that you're receiving. It's pretty much very similar to that. Now, if you think of that as a series of those pulses that you're sending from the radio station down to the radio, then chop it down in time. Those blocks of time is what we call it as block. And each block could be either working with the RF coil or the gradient coil or the receive, which is the ADC. That is called an event. And each event has a shape. Maybe I want to send out a long pulse, maybe I want to send out a short pulse. So that's the kind of block events and shapes. Here's how it would look in code. If you go through the first one, you have horizontally each one is a block, and then within that one horizontal row, you have these columns. Each column is like an event, and each event has a shape. So it's very simple to understand, right? If you're thinking of a wave that's moving, you chop it down in blocks of time, take a block and see which, am I playing this block on what coil, that's the event, what is the shape, does it go like a triangle wave, does it go sine, does it go rect, so that's the block event shape. On the other side of the spectrum, you had this tool called the graphical programming interface, where you could build a UI, a user interface, and then once you build a user interface, you want to kind of configure it to what you want to do. For example, if you had a new app on the phone, then you went and you personalized it. So the second step is like the personalizing. And once you start personalizing, then you get a bunch of options. Might be colors, might be avatars, and things like that. So that's the node widgets and widget configurations that you got with the graphical programming interface. So the cool thing with this is you didn't need to know the back-end coding. You could just put a bunch of blocks together and make things work and reconstruct in your language. This is also available for download for free, and if somebody is interested in the general area of, I'm more interested in once the data comes in, can I reconstruct the data? Then this is one of the tools that you can use. So my PhD student started thinking about this and tried to kind of get the pulseq and the GPI, kind of together so that you could have the acquisition and reconstruction together. So he put these things in a way that the acquisition and the reconstruction mirrored each other. With that, we've given this to a bunch of students at the undergrad level who can put blocks together like in Legos, and then be able to do the whole pipeline of once the hardware is ready, get through and build the whole software pipeline starting from simulation all the way to visualizing data. Here's a snippet of how it works for a sequence called gradient recall decode. What we do here is essentially say we have the gradient coil, we'll apply a pulse on it, it will kind of dephase the signal, and then we rephase by changing the polarity of the current of the coil. So, it's simply put, if you think of a motor, if I put one kind of current, the motor goes forward. If I put the opposite polarity, it goes backward. So by doing that forward and backward, you can create what is called an echo. And here's a simple example of gradient recall echo. And you can put this together in about 9 blocks. So that's how simple it is. If you try to do this on a standard clinical scanner, it will take you at least 6 to 7 months before you get to this stage, because you have to learn the tool and it has its own benefits and disadvantages. What you do here, again on the right, I don't think it's legible, but on the right is the Python code equivalent for those blocks. So if somebody was more interested in scripting, you could use the one on the right. On the left, you basically pull these blocks and say, I'm going to just concatenate these blocks in Legos, one next to the other, and then the last one where you see write sequence actually gives you a file that you can take, plug into the scanner, and play. So we went about doing that. This was in India on a GE system, a 1.5 Tesla. On the top you see the bunch of blocks in the GIE. You do need what is called as the interpreter. I'm yet to figure out what system you have here. I think it's the Kia. If it's Kia, we do have an interpreter for it called the Seek to Prosper. Prosper is the programming language that sits on that system. So Seek to Prosper is something that would be useful if you guys wanted to program in Python and then play it on the system that Eunice, Tom, and everybody is putting together. We acquired some images too, and we compared it with the vendor, which is GE, and showed that you can acquire identical sequences between the two. This was at 1.5 Tesla. You can use this tool either on a Mac or on the Windows. We've shown 3 particular sequences. I'm happy to go into the details, but there are 3 different ways. One looking at white matter, the other one looking probably more interestingly at gray matter and certain hyper intensities in white matter, and then the last one is super rapid scanning, let's say. We benchmark that with vendors using MATLAB, Python, and this graphical programming interface on 2 operating systems. So we've added to that already existing huge number of tools, we've added 2 more. The good thing though is as you go from left to right, you can see the bottom one actually check off many things that you want to do with an MR scanner compared to the rest. So that's been the contribution. So if you wanted to pick one tool, for example, for machine learning, today probably the most unanimous choice would be TensorFlow. So this is similar to that if you wanted to develop things for your scanner. The next question that we asked, and at the bottom here of the publication, there's also another publication for the first part. We said, well, if you do open source programming, what if somebody puts in things that are not good, not safe, and does something either to the hardware or worse, does something to the person or people who will get imaged. So we started thinking about those and started validating these tools. So we looked at both aspects, hardware and image quality, and also safety, because safety is a big concern. And for different kinds of sequences, here's the problem. Siemens has a scanner, GE has a scanner, Philips has a scanner. But the person who's going to get scanned might be in Entebbe one day and then maybe in Mbarara in the next. Just because he moved from a Siemens to a G scanner, if he doesn't get the same sequence and the same kind of study, it's tough to compare between scanners. So that's called harmonization. And one of the benefits of open source imaging in general is you can harmonize. You can play the exact same sequence on different vendors. Right now, we can play the same sequence on a GE, on a Siemens, on a Bruker, with some limited capability even on the Prosper, which is here. So I'm interested to explore that. This is another way to look at what are the different tools that allow you to program scanners. We are column row number 2 with PyCon-Seq, and like I said, all you need is a browser to get started. The others don't. So when I say zero footprint, meaning do you have to install something on your laptop or not to get started? Our tool does not require you to install anything on your laptop. All you need is connection to the internet, and that too not significantly something that runs movies or whatever. I'll skip this one. This is mostly about how we go about doing that. Here's how it works right now. So we did some sequences at our University of Columbia on a 3 Tesla and then shipped it off to Lisbon on another continent for 1.5 Tesla. We tried 2 different kinds of sequences where we developed, we let them use it, gave us some feedback, and then we're trying to figure out whether you can play the same sequence or not. So this is what you did on the computer. We were able to simulate it, and then show this is the kind of images that you're going to get. So here's the comparison. A is using our tool. B is what Siemens actually produces from their own scanner. And the last column is the difference between the two. So like you can note, using this open source programming tools, you're getting pretty close to the vendor image quality. There are a bunch of tools, tests as well. So I'm from North America, so American College of Radiology is the standard there. So they have a bunch of tests to say whether a particular sequence works or not. So we've actually benchmarked those tests, and you can see that we're doing okay there as well. This is a continuation of the same ACR tests. In some more. Okay. An exciting thing that's happening in magnetic resonance over the past, decade and a half now is quantitative imaging. Is if you see a car going on a highway, you'll say it's going fast. That's one way of looking at things. The other way of looking at the same thing is to say it's going at 85 kilometers per hour. So the difference between qualitative and quantitative imaging is being able to identify particular values. So here what we're showing is a standard phantom which says what should be the T1 and T2 values in seconds. So you're not saying whether it is slow or fast, you're actually quantifying that in seconds. And you can see that the sequences do pretty well with what is known as the R-squared fit to show that you can rely on these sequences even if you were to do quantitative imaging. At low field, this is very relevant because of the following. Because it's low field, you probably can image multiple times, but you probably won't get the signal to noise ratio as that of a 1.5T or a 3T. So if you have quantitative imaging, then you can actually pick out small changes over time, which is super meaningful. For that, you need tools like this that can work on quantitative imaging. Here are the results comparing those quantitative imaging and qualitative imaging for safety as well. where you see the specific absorption rate with our own open source tool, which benchmarks again to a Siemens and a GE that shows that if you use our safety assessment tool, you should be okay. Um, so within the community, people have picked this up. They use this tool to do a whole bunch of different things on autonomous MRI, pulse sequence diffusion, spiral fMRI, seek to prosper, which I think is going to be useful for this site. Pyrogenesis, CEST imaging, SIGPI, short echo time sequences and the like. Here are some references for those works, and I'm sure once the slides are available, you should be able to look at them. Yeah, here's how to run this tool. If you are already aware of how to use Python, you can just get into shell and type pip install PythonSeek. It should be good to go. How many of you have Google Drive here? Google Drive accounts? Okay, great. So if you go to Google Drive and then right click and say open with and more apps, you will see this thing called Google Colab. It's free, it's by Google, it's available to everybody. And once you have that, you can start running these sequences on that. So that was part of the demo I wanted to do. Maybe either during the latter half of today, tomorrow, anytime in this week. If you're interested, please drop by. I can just sit on your laptop quickly and show it to you and get your first pulse sequence on gradient record echo going. That was part of my demo, but I'm happy to do it offline as well anytime. You can upload a network, import a network. That's the best thing about it. If somebody on this side was developing a sequence and you wanted folks from the other side to look at it or refine it or use it, it's exactly the same as a Google Doc. You can collaboratively make these sequences, edit these sequences and play these sequences. So I'm excited by the prospect of doing this in a collaborative setup. This was the demo. I will skip this for now, but I'm happy to do this next. The last I have quite a bit of slides on this virtual scanning, which I think is very relevant to this audience here. Um, this is again on the web. You don't need to do anything. You can again launch this with pip install, or one person could launch and a whole bunch of others could access this. The idea here is, let's say you didn't have the hardware and you wanted to simulate all of this. You could do this using what we call as the virtual scanner. In fact, this started out because Jonas put out a challenge at ISMRM to build a tool for education and research at the same time. So we started this, and this has been going on since 2019. This is called the Virtual Scanner Project. It's open source, it's web-based, and supports education and research. So, just to give you a background on why we got motivated with Jonas's challenge, the ISMRM Junior Fellow Challenge 2019, is the accessibility to MR scanners, like you can see, is diverse across the globe, and specifically where we are today, the prevalence is low. So when you have a virtual scanner, you can actually start playing around and visualizing. So all you need is essentially a laptop or some computing device. We've gone through two versions now, and we are now also integrating this with another education scanner called the tabletop scanner, which is at 0.40, has a small 10 mm bore, comes out from MIT and Harvard. We have some colleagues there. So we are also plugging in with that hardware so we can play that on the education scanner. Version 1 was mostly focusing on MR students, and that's why I'm excited to be talking about this today to you. we've continued that in virtual scanner 2.0, where we've shown that you can use this as a digital twin too. This was ISMRM challenge. This was the concept. This is how the UI looks like, similar to how the user interface would look like on a clinical scanning console. It has a bunch of components in there for you to look at. You can, like I said, you can do acquisition, you can do reconstruction, you can also pass images back and forth, you can test out your signal chain, RF transmit and receive. The way you would go about doing it is you would log in. I think the new version does not have the Columbia logo anymore, but you log in using an internet browser, and then you get to the registration page. This is very similar to what you would do on a clinical scanner. So you log in and then you have registration details. Instead of a patient, we are registering a phantom. And you have a bunch of options on the phantom here. Geva, my student, has good creative skills, so she's made this phantom with a bunch of balls with different copper sulfate concentrations in them. But the experience is very similar to running a scanner. So those are the regions. On the left you fill out the details, on the right you visualize the phantom. And then this is how your scanner would look like if you were to use, for example, I think this is heavily motivated by looking at clinical scanners across not one particular individual vendor but across. So you would have this acquire tab where you would set what parameters would you want to acquire the sequence on. And then you can start, like the simplest sequence to start off is a gradient record echo. So you pull that, you add it, and then you start configuring that to play. And then you can analyze your data too on the same tool. So this is like mocking the whole scanner on your laptop. It runs what is known as block simulations or extended phase graph simulations, the kind of simulations that enable you to envision what the data would look like. Here is an example of curve fitting for looking at what this is the ISMRM wrist phantom for relaxation. If you want to get into the research mode and say I want to look at designing RF transmit and look at the SAR profiles and things like that, you could do that too. You could also look at advanced reconstructions using deep learning, where we've shown an example where you can undergo aliasing because of undersampling in K-space and be able to reconstruct original images as well. So all of this again is on the browser. Once you install it, you can get going. The good thing about virtual scanning project that we are really proud of is the documentation that comes with it. We have spent quite a bit of time to make sure that you have sufficient documentation, whether you want to be an end user, whether you want to be a developer, or you want to have different kinds of options to get started. You have it on Read the Docs. So we also have a way wherein we've leveraged other existing tools called the GEMRIS, which can do fancier MR simulations. So we found a way where we can feed the seq file and use GEMRIS's way of simulating certain effects such as flow, diffusion, and the like, and still be able to pull that back into virtual scanning. Here are some sample outputs for evaluating one of the sequences called epiplanar imaging, which actually won the Nobel Prize for Peter Mansfield and Paul Lauterbach. But yeah, so this is also a validation of looking at how the simulation tool can actually be used. um, to do some of these more fancier things and compare them to the real scanner as they go. In version scanner 2.0, we've taken this one step forward. What we've done is to say, okay, I'm producing this bunch of simulations all on the computer. Does it actually work in the real world, and does it make sense to form a closed loop between the virtual world and the physical world? So we've kind of integrated the digital twin using this virtual scanner with the physical twin, which is the MR scanner. So you do these experiments in your lab, then you want to move it and then see whether it makes sense on the real scanner. That's one way. The other way is to also keep learning from the real scanner and be able to debug the real scanner by learning from what might have gone wrong with it. So we've demonstrated a case wherein we've picked up phase artifacts from the real scanner and fixed it. So we've done a bunch of simulations for different kinds of sequences and also different hardware features. So this is mostly what it can do. I'll skip this slide, but you can do hardware simulations on the transmit and receive side. And we have a bunch of notebooks, like Jupyter notebooks, that you can try out. Depending upon whether you are interested in hardware or RF simulation or acquisition or reconstruction, you can just get started by playing around on any of these Jupyter notebooks, which is again a Google Colab notebook. Finally, we had a high school student this summer come and help us develop what we are calling the tabletop games. This is a bunch of games to introduce MR to students who never had any kind of brush with MR before. The way we want to make it work is we want to use a Piper-Seek experience, the virtual scanner ability to actually program a tabletop scanner, which is a little different from what you guys are doing now. But with the Seek to Prosper, you could replace the tabletop scanner with the low-field scanner that you have here. This is a snapshot of the other one, which is the tabletop scanner. It's slightly higher magnetic field at 0.4 Tesla now. Sorry for the slide being backed up. But it's also open hardware and a bunch of specs, which 0.02 to 0.40. We'll kind of skip this one. It's trying to kind of segment what you can do just on your laptop and where you need to hook up to the hardware. But I'll talk to you only about the virtual mode today. Skip this one here. So it has these 8 games. This is all from a student Dewa Tom. So she named this Mount Residence. And you can either climb 1, 3, 5, 7, or you can do 2, 4, 6, 8 as well. The 2, 4, 6, 8 are advanced games, 1, 3, 5, 7 are the basic games. Game 1 is about FOV and resolution. So if you were new to imaging in general, MR in particular, this is a nice way to get started. And we've kind of tested this across 3 different tiers of MR expertise, starting with high school students, undergrads at Columbia, and PhD students at Columbia. So you're learning about field of view, you're learning about resolution. This is one game. The cool thing that they've been able to implement is if you do end up answering all the questions and learning, I mean, it's basically instructional. You don't need to have any kind of prior knowledge to play these games. So it's instruction based. You go and if you don't know a particular item, you can go and actually, let me see if she's highlighting that. So there are user inputs, display regions, and then instructions and quiz. So you can actually walk through, learn definitions. If you want, you can go more in details on this and then be able to answer the quiz. The cool thing I like about it is when I got everything right, there is confetti that showers. So that was the cool thing for me. But I can go through each of these. The second one is about how you look at contrast in MR. This is probably the most important piece if you were to do any kind of engineering, biomedical engineering related to MRI, is to understand what is different kinds of weighting, how do you achieve that. So this lets you play all of those. Um, Again, you have the similar kind of structure. Uh, Once you've got those things, Gavas come up with these cool names, sometimes too loud, like protons got moves. So you can actually start thinking about how magnetization moves, the net magnetization M0 moves in 3D space by looking at the magnetic field, the radio frequency, you can hear it out, and then you can learn. This would be a very good start for people wanting to get into this field without having to spend a lot of time reading into books, which you necessarily need as the next step. But this is a nice way for you to start playing some games and trying to learn these ideas. Uh, Again, projections, Paul Lauterbach again. So this is the two water bottle fountain, trying to look at the projections and then testing the results out as to whether you can understand how these projections work out. The good thing about this, for the risk of repeating myself multiple times, you don't need to have any kind of knowledge before starting this. The idea is for this tool and these games to be able to help you get there. This is about how this whole thing has been implemented in terms of the front end that you see, and the user interfaces are quite intuitive and interactive. And then at the back end, you have the Python working constantly with Flask, and W forms and Jinja. So I think, yeah, so it's taken quite a while. With that, I just summarize. Again, if you're interested in the virtual scanner, tabletop games, or the games in general, uh, definitely meet me sometime, probably tomorrow. I just make sure that I have a version on mine running, and then I'm happy to set that up on yours as well. Um, yeah, so just to summarize what I've been showing, um, we've developed methods, mostly tools right now that I've spoken here on web accessible, free, open source, acquisition and simulation and MR education tools. It does support different kinds of hardware. You have at least 3 open source hardware platforms that this can support. Then you can integrate this with other third-party Python libraries. We've shown a couple of examples. Um, you will find exhaustive documentation of all of these tools on our GitHub webpage. Like to call out Pawan and Ilvin. Gerua is putting a lot of work. Shravan's been developing the Michael Seek tool since 2017. Marina has contributed a bunch to the front end. Um, a student from Bronx High School who interned also. Rishi, who's not here, who also helped us. Here are different collaborators that we've been working with, and you can see some familiar faces. I'd like to shout out Godwin, Andrew's team, with Tom here, a bunch of collaborators from different countries. I'd like to thank my funding sources, and with that, I have a couple of shout outs. If anybody is working in the area of machine learning and MRI, we have an editorial in Frontiers, Autonomous Magnetic Resonance Imaging. Godwin is also working on this special issue. There is also an issue going on in NMR and biomedicine that we're coordinating called Accessible MRI and MRI for the World. So please feel free, if you have any contributions, to submit. We would love for people from this part of the world to put things in there, so that there is equal opportunity and representation. With that, I'd like to end, and if you have any questions for me, or if you want to set up some time, either for the pipe and seek demo or the virtual scanner tabletop games or the virtual scanner demo. I am more than available until the end of the week. Thanks again.
Are you ready for me to start?
Yes.
Yeah? Okay. I just wanted to, before I start, I wanted to also say that opensourceimaging.org is a really cool place to find a lot of these open source tools. And it is a great idea to try to collect all these things in one place. I also have the same frustration because you guys never know where to look for things. So I think Lucas is also putting together something like a wiki for open source imaging.
There is a wiki.
Yeah, there is a wiki, I think. So if I remember correctly, if you go to opensourceimaging.org, you can even sign up for the mail list to receive information. I really encourage you to do that. It's a really cool community and it's growing. And Lucas has an infectious personality, so people are going to definitely jump on to that. So yeah, definitely do like, sorry, I didn't catch your name. Sairam. Okay, definitely follow his advice. Okay.
It actually rhymes. Sairam.
So that's my plug for Lucas. I am definitely signed up for open source imaging. Okay, so what I'm going to talk to you about today is more on the application side of low field MRI. And this is a study that I did with the help of all these wonderful people down here. And actually, to me, this is a very interesting data set because it's using CT images that were collected here in Uganda in our partner location, Cure Hospital in Bali. And we would love to have low field MRI images of infant hydrocephalus, but those don't exist anywhere in the world. So we use CT images, and those barely exist as a repository. So this is really precious data, and we're really thankful for all the folks at the Cure and here at Musk too, for carefully curating that data and contributing to this. So just to start off. So a little bit about me. I currently live in Paraguay. I was looking for my own photo, but I had to rob this from the internet because I didn't have one as pretty as this. But we have these beautiful trees in Paraguay that bloom pink and yellow and white, depending on the variety of the season. I just love it. I don't know if you have also beautiful plants here. Some of the same plants actually that I have in my garden as well, I've noticed here, which I thought was really interesting. But anyways, this is one of the things I love about Paraguay and Uganda, is the beautiful nature that exists in both places. This is my family, my wife, Carla, my daughter Adriana, my son Oliver, very satisfied with his haircut in this picture. And actually in 2018, Tom and I visited here, visited Jones' lab, visited this building, and I think they were just putting in the equipment into this lab when we visited, actually, all the mechanical engineering stuff. We arrived when the building was starting. So, yeah, maybe a little more hair, a little less belly fat, but more or less the same people in 2018. So I'm very excited to be here again for the second time. Okay, now on to business. So hydrocephalus, it's a real problem in the global south, and especially in sub-Saharan Africa. We estimate more than 400,000 new infant cases per year, which is astounding if you think about it. And so this project, I think many of us are here today, at least downstairs, building that MRI because of this. Steve and Dr. Kulkarni and Dr. Worf, neurosurgeons that were working, in the Cure Hospital from time to time, and they noticed, all these cases of hydrocephalus. They got curious about, how to treat these better. So that started this study. And then they noticed that we only have CT available to image these infants. wouldn't it be great if we could use MRI? And that's how they started pushing for this low-field MRI technology as it relates to hydrocephalus. And really, that's kind of the roots of why I'm here, for sure, and John's as well, I believe. But as you can see, this is a real problem that we have. So in the Cure Hospital, which is in Mali, since 2001, they've treated more than 18,000 hydrocephalus children. And the largest group we see here is post-infectious hydrocephalus. I think congenital hydrocephalus is more in the United States and Europe. I'm an engineer, so I'm just repeating what I've been told at this point. Feel free to ask questions that I may not be able to answer. So for treating hydrocephalus, and this is important, you have to pair diagnostics with treatment, right? So there's kind of two options. There's a shunt, where the surgeon will go in and place this shunt into the fluid space. And I guess I should say, first of all, hydrocephalus is this water in the brain. You've seen these kids with these really big heads. Basically, they can't clear their CSF, and so it causes their heads to swell. And because they're so young, their skulls have not fused yet, and so their heads can just get huge, right? And the worst part about that is what is happening to their brain development during this period of time, right? Here's some CTs of these cases, and it's horrible. You can see the dark spots are the cerebrospinal fluid, and these little white tracks here in the brain. It just doesn't look good, right? So to treat it, you must treat it, otherwise these children will die. They put the shunts in and try to drain the fluid to another part of the body. Well, that's okay, but typically these shunts fail eventually and they have to be revised. This is very risky for patients to develop infections. It's not a great way to do things. And so the doctors here with Steve and Ben and Dr. Carney developed this other method, endoscopic third ventriculopathy. Can't believe I actually got that out of my mouth. ETV, I'll call it from now on. Where you actually go in with an endoscope and kind of burr holes in these different channels of fluid to connect them. And then you target this little area in the base of the brain to try to let the fluid drain naturally. You can't do this for all patients, but for a lot of the patients you can do this. And actually now we've been following these kids for I think close to 10 years, and it's looking like shunt placement and ETV are equally effective. Neither is particularly better than the other. I think in some cases you might find one is better than the other, but in general the outcomes look the same. Unfortunately, the truth is the outcomes look bad in both cases. And so really what this group, what the medical side of our group now is looking into is how do we prevent these infections from ever happening? Because it's really hard to treat this condition effectively. But we still have these cases. The treatment is important. So you need biomedical imaging in order to be able to plan either of these procedures, right? You've got to see what's in the brain before you go inside. You don't want to go in blind. You can't go in blind. And as I stated, CT is what they have available in the Cure, and actually in much of the world is what they have. So technologies you can use to do this. You've got ultrasound, very affordable, very portable, but you can really only use it in the first year of life before the skull starts to fuse, right? And that can be bad because if you have images in the first year of life that you've used, and then hopefully the child survives the first year, you don't really have a good comparison. You've got to use something else afterwards. So it may be difficult to tell if you need to revise the shunt or if you need to go in for another intervention. So it's not a great option. CT, of course, is what is here and is in much of the low and middle income countries for brain imaging. Good contrast, good SNR, expensive, not so available globally. And there's a significant known risk to children because of condition. We like to say there's also a risk to adults. I think probably people would be willing to admit it's not, we don't have these huge number of cases of people that have had CT as adults without big problems, but for kids, you would really not want to dose them with radiation multiple times early in their life. course, MRI would be the gold standard if it wasn't so darn expensive. It's very safe, very versatile, but it can be up to $1 million per Tesla. And that's just biotechnology. So if you've got these 1.5 Tesla machines, 3 Tesla machines, you can expect to pay over $1 million to own it, and then probably hundreds of thousands a year to operate it, right? So this is not technology that is for everyone. You can't replace it with low field. There's certainly cases where we need it, but it's just not viable in most of the world. And that's just a fact. So interestingly, I'm going to close with what's happening, sorry. Interestingly is the wrong word, but if you do look at where MRI and CT exist globally, you can see the dark green. I don't know if you can read these numbers, but the dark green indicates a higher density of these imaging technologies per population. And if you consider that against where the disease that we need these technologies for exists globally, it's almost the inverse, right? And this is not only true for hydrocephalus. You see this all over the place. The good technologies are in the places with fewer diseases and fewer incidents. So we've really designed medical technology the wrong way around, I think. We've started at the top, and it doesn't trickle down to the bottom because it's too expensive, it's too complicated, too difficult to maintain, right? So you could do this for stroke, all of the major diseases that people die from in the world and create disability. You're going to see the same trend. So this is a problem. And so maybe this is a stretch, but I kind of like to propose to you that we could think of high-field MRI as an overly complicated tool for some relatively simple tasks, right? If this was the way we had to get toothpaste on our toothbrush, probably very few people would brush their teeth, right? And this is an over-exaggeration, but it's kind of the same thing. We've got really nice, really top technology that clearly most of the world can't use. And we need to start thinking, can we simplify this technology and cover a lot of the cases that people need, without pricing ourselves out of the global market? Hopefully that doesn't offend anybody. So why does medical technology, including MRI, fail in low resource areas? Actually, there's a group called Engineering World Health, which started at Duke University, I believe. Very cool institute. I believe Ivan's not here. Ivan said he took part in one of the Engineering World Health Institutes. And it's really interesting, you should look into it. They collect students, professors, professionals, I don't know, from all over the world, whoever wants to sign up for one of these institutes, and they send them to some of their partner hospitals throughout Africa. They've got some in Central America too. I'm not sure about Asia. But they'll send them to these hospitals, they'll train them how to basically, I think we have biomedical engineers here, they'll train them in biomedical engineering for a few weeks, give them some language courses if they need it, and then they send these folks into the hospitals to help fix equipment and document what's going wrong. This is something that we often don't do, right? And so they've curated all this data on why the technologies are failing, what's going wrong, which technologies are failing. And basically it's things that probably all of you know very well. Initial cost is a problem, spare parts is a huge problem, right? Consumables, so for MRI we're thinking liquid helium. Training, reliable power. Sometimes the technology will come in and it won't have a training manual in the language that it's going to. And so even the folks who are perfectly capable of fixing the equipment don't have the information they need to do it. It's really a travesty. And so for MRI, you start thinking of field strength as proportional to the cost of the technology, proportional to the image quality too, right? But maybe inversely proportional to the sustainability of the technology in a global scale. And that last part is really important if you actually want to use it in places that have fewer resources. So there are low field systems in existence, and I really need to update this photo of the top system, which is the one that we're actually building downstairs right now. We finished the magnet last night.
That's night.
Yeah.
You finished it?
The magnet.
25 weeks.
Yeah. I should have saved, I have a picture at the end I should have saved it for last, but anyways. Yeah, very exciting, very exciting. So we've got these systems in existence, and they have varying degrees of quality aspects. These are actually really old images from the system that's sitting downstairs. We can do much better now. A group at MGH has been working on this permanent magnet system as well. We've got some nice bright images. Many of you probably have heard of Hyperfine. They're kind of leading the market in image quality right now. I've got some questions about their image quality, but it's a really nice system. It's FDA approved. You can go put it in your hospital and use it right now if you want to. And that's very exciting, actually. And we also know from the literature, I mean, MRI started out as an MRI, right? We know from the literature that lower fields can be as diagnostically accurate as higher field MRI for a variety of purposes. And I think the most current, the most interesting ones right now are many of the studies from folks using Hyperfine, especially Kevin Sheff, who's a collaborator and a colleague of ours, who's been looking at stroke and different effects from COVID with these systems and have shown to be quite useful. So we know these things can work. There's a lot of evidence for that over the years in the literature too. So why not? Why not try to use them? Here's a side-by-side image of the same brain on a 3 Tesla system at Leiden and 50 millitesla system that's currently sitting downstairs, also at Leiden. And I also would comment that Tom would want me to put a much nicer image on this now because the system's come quite a ways. But even so, if you're thinking about hydrocephalus and you see these two images, the question is, which one of them is good? And we can all clearly see that the brain at 3 Tesla is a much better image. But if all you really need to see is where is the fluid and where is the brain, the image on the right is probably good enough. But we don't really know, right? We haven't really looked into that very carefully. So all we know right now is that higher quality images do not always lead to higher diagnostic accuracy. Depends on what you're looking for, right? And there are low field systems that are good options for clinical imaging in low and middle income countries because they have a lot of aspects that are required to actually put them in a clinic, right? But the question still remains, what is good? What is good enough, I guess? So I did a little study to try to tease that out. And what I did is we think of image quality perhaps as a combination between resolution, contrast between tissues that you care about, which for us right now is brain and CSF, and the amount of noise in the image. You can kind of imagine it could be this kind of image quality space, right, where contrast can reduce on this axis, noise may increase on this axis, resolution may increase on this axis. You're going to have this wedge of useful image quality. Right? As resolution increases, we can stand a little less contrast, a little more noise, but really going to be severely limited as we reduce our resolution. And then there's going to be a whole lot of combinations that are just not useful, probably an area in the middle that we're not really sure about, right? So if we take out a single plane of this image quality space, we can look at some examples. I'm sure this is looking quite washy for you guys out here, so I apologize if you can't see the details. But we can see noise increase, and we can see contrast reduce, and then both at the same time, right, along this dimension. And we want to investigate where are these lines drawn? Where is the line between a good and a bad image for hydrocephalus treatment plan? We can take it a step further even, and we can say, well, let's say we use some machine learning to improve the image quality. Could we actually take an image that's in the bad region, put it through, say, a deep learning network, and output an image that is good enough to use. And we did this too. So you can see here, once again, I don't know how well you can see the detail, but way up at the top there is the enhanced version of this image down here at the bottom. And it does look a lot better. But if we look at it next to the ground truth, it looks a little different than the real ground truth image. I had the advantage of artificially reducing the quality of these images so I can go back and look at what the original actually looked like. So maybe there are some questions there, right? What have we actually done in the image when we do this? So for the experimental design, we had 90 different patients we could pull from. We took 80 of those patients and we made those training images. So we were going to build our deep learning network, train our deep learning network on these images. And we kept these 10 that I'm showing you right now as the test images, right? So you always want to separate your test images from whatever you train on when you're doing machine learning. And I took the centermost slice from each patient to use for this, because using all of the slices, I'm going to show these to some surgeons, and using all of them would have taken a couple of days of the surgeon's time, and surgeons don't have that time. So we had to reduce the amount of time a little bit for these guys. So this was the way we set it up. We adjusted the resolution of the image by downsampling using bilinear interpolation. This is a very simple way to do it. We thought of the bilinear interpolation sort of as encompassing the partial volume effects of, two side-by-side pixels where it was a different grayscale value, you would end up getting kind of the average of those two. And I used MATLAB to do all this. I went from 512, which was the native, about a 24 centimeter field of view, to 128, 64, and 32. I chose these because I thought these were likely good resolutions for low field MRI. I think 128 is actually probably what we do right now on the system that we're building downstairs. I added noise based on what we know to be CT noise, which is Gaussian noise with the mean equal to the variance. And here we had to experimentally determine the maximum amount of noise we could add in resolution so that we could actually see this line between a good image and a bad image. If you add 0.13 standard variance of noise to a 32 by 32 image, it doesn't have the same visual effect as for a 512 image. So we had to kind of experimentally determine where we thought this line was going to be. So these are the max noise variances that I used for each resolution. Reducing the contrast was something that I actually struggled with for quite an amount of time, because most people are trying to enhance contrast instead of reduce contrast. So the first thing I did was, fortunately, I was working with these really excellent machine learning people, Ichan and Kat Cherukuri at Penn State, and they did all the machine learning stuff ahead of time. So I had the added benefit of already having these segmented in the brain and CSF. So I pulled out the histogram gray values of the brain and the CSF, and I thought, well, I'll just start kind of overlapping, right? So I want to reduce the average grayscale value between brain and CSF. I'll start overlapping. When you do that, you end up highlighting the boundaries between brain and CSF, and so it becomes almost easier to pick out the difference between the two. So that, well, that's not going to work. So I come up with this thing that I call histogram compression. And instead of overlapping the grayscale values, I start compressing the bins of grayscale values iteratively. So I don't actually change the boundary between brain and CSF. I just start squeezing the grayscale values into smaller and smaller histograms. And it really effectively reduces the contrast. Here, it just looks like a gray smudge. This is way too much contrast reduction here, but this is the extreme example. So this is how I ended up reducing the contrast. So I can do this iteratively. And then what I can do is I can calculate the median grayscale value of brain and the median grayscale value of CSF. And as those two numbers get closer and closer together, I have this continuous range of contrast between the two that I can adjust. So I can sort of define the contrast between those two on a continuous scale. So for training the machine learning networks, this is very time consuming. We can't do it for every potential combination of noise and contrast reduction, right? So for two different resolutions, 64 by 64 and 128 by 128, I chose 7 locations throughout the noise added and contrast reduction plane to train networks. So what does that look like? So for network 1, for example, I had a noise added of 0.25. So this is normalized to the maximum value for the resolution. So a quarter of the way to the max, and then about a quarter of the contrast reduction. I apply that image quality reduction to all the images in the training library, and then I train a machine learning network. So now I have a machine learning network trained for images that have this quality measure. I can put my test images through it and see what comes out. Does that make sense? So I do that for 7 different network locations across 2 different resolutions. And I've got 14 different machine learning networks that I can put images through and take a look at the output, right? So you can notice here that network 1 is the least quality reduced network. Network 7 is really that. It's all the way, I think it's close to the maximum contrast reduction and noise added that I can possibly do. We would expect those images to come out worse, right? Feel free to stop and ask questions along the way if you need to. I know this is a bit confusing sometimes. Yeah?
Thank you for the first question. There was like both an outline of images where you're trying to take a good,
Yeah.
a good image, or the one for the outside good images.
Right.
And then you now enhance it, then you became the
Right.
How about the one, if you had chosen the one which was, what's the degree of enhancement? Does it get close to 1.5 or 2.5 or something?
I mean, if I choose an image that's already good, we did that too. You'll see. The results are coming up. Yeah, we did that. So actually, this is a good point. So I chose these locations expecting that, maybe even hoping that the line of good versus evil would be like somewhere here, right? So I wanted to have some networks that were in an area that probably if people saw the degraded version of the image, they would still say, okay, that's all right. And then I wanted to see how the enhancement changed their opinion about that. Then I also wanted some networks that were in a region where if people saw that image, they would say, no, there's no way I can use that, and see if they didn't like it better. So I wanted to kind of look at both at the same time. But the results are coming through. If it doesn't answer your question, you can ask me again. So we recruited 3 evaluators for this. Matt Polcarney, Benjamin Wharf, Steve Schiff. These are all neurosurgeons who have experience treating hydrocephalus here in Uganda. So that was kind of important to us in the sense that we wanted to have neurosurgeons who understood the difference between having the availability of a really high quality image all the time versus having experience where you just can't treat because you don't have any image, right? So we thought that would sort of make people a little more amenable to looking at high quality images and really being able to say whether they could do something with it. So this could also be a potential bias to the data, which you should be thinking about. Is that if we show this to neurosurgeons from the Netherlands or the United States, they would probably say, all these images are terrible, I'm not using any of them. And they could be right, but they have access to the technology to make good images all the time. So it's a little bit different in terms of what you might be willing to work with. Yeah.
The previous slide. The previous slide.
The previous page. This one?
Yes. What is the graphs I've been seeing for contrast reduction and then noise addition? Actually, realize when you do contrast reduction, you delete some of the important information in the signal. So should I assume that the contrast you're reducing is actually balanced by the noise you're adding?
It's worsened by the noise. You're absolutely right. If you have reduced contrast between the tissues that you're trying to look at, you're losing valuable information, right? And then if you throw noise on top of that, You can't even pick out
the information.
Yeah, you can't even pick out the information that's there, right? So this is the question: is we know low-field MRI has lower quality images, but how much contrast reduction or noise added can we take before we can use the image? And as a sidebar, I should say, low-field MRI doesn't necessarily have like this linear decrease in contrast from high field. In fact, we might have better contrast in some cases than in high field, because contrast doesn't really work that way. But I wanted to just look at the spectrum and see what comes out, rather than try to simulate what low-field MRI would actually do, since I don't even have low-field MRI.
So, can you draw a relationship between contrast reduction and noise addition? Is it direct proportionality or
Not necessarily. I wouldn't say that, anybody can correct me if I'm wrong, I wouldn't necessarily say that the noise has any relationship with the contrast that you can produce. My view was, let's explore this space of contrast and noise combinations and see where we can handle noise and contrast reduction, see where this line between what we can use and what we can't use comes out. So I was looking at it kind of disassociated from any particular technology. I was just looking at what is actually in the image that these surgeons care about. That was my goal. Does that answer your question? Okay. Tom, I think we'll talk later more about contrast, and you'll see what I'm talking about, where it doesn't flow like this in an MRI. Okay, so I made an app in MATLAB to show these guys, these surgeons, and it was in two parts. And in part one, I just asked them which image is useful, and they would respond. And then if all three, and they did all of it, they did this separately at different times. If all three experts agreed that a particular image was useful, that image would get a 3. If one or two would agree, the image would get a 1 or a 2, right? So it's just additive. And if all of them agreed that it was not useful, that image would get a 0. That's how I scored the images. So you can think of this, my little plane of good, uncertain, bad. This would be the green, the good. This is kind of the uncertain region where not everybody agreed, and this is the bad, where everybody thought, no, we can't use that image. This is what the panel looks like. I displayed 4 images at a time, and they didn't know it, but there was always one machine learned image in each panel that I showed them. So I think it was this image in this panel. So ahead of time, they didn't know that they were looking at the machine learned images. And I just asked them to click whichever one was useful. So they would do that and they would submit it. And I put a little progress bar so they would have hope that this would end someday. It was very long. I think there were 420 degraded images and 140 machine learned images they had to go through. So this is what these guys said about these images. They all liked the enhanced one. This is not feedback that I gave them. I put this in the section. They all liked the enhanced one, which originally had 60% contrast loss. None of them liked this image. It's very noisy, as you can see. 71% contrast loss, quite a bit of noise for a 64 by 64 image. They all like this image, which had no added noise, 42% contrast loss. And only one of them liked this image. And here, I apologize if there's any surgeons in the room, but I mean, come on. These guys are so confident, aren't they? They can use this image. But one person said he didn't like that image. 2 of them said they didn't. So here's another example. What would you guys think? Can you see it well enough? What do you think about the top left corner? Who thinks that could be used? Raise your hand if you think top left corner is useful. All right. I would score that probably a 1, maybe a 2. What about top right? No. Okay. We think 0. What about bottom right? Show of hands, bottom right. You guys are pretty conservative. Bottom right, yeah. Yeah, sorry. Maybe I should point this one.
Yeah, that's one. Yeah, I think
Pretty much sure. Okay. What about this one?
somehow.
Mid-range, yeah? Okay. See what the surgeons thought. Yeah, more or less what you guys thought, right? Actually, almost exactly what you guys thought. This was a machine learned image, by the way. And yeah, everyone said this one was okay. One person said that was okay. Everybody hated that one. So more or less what you guys thought, which is interesting to me. Are any of you neurosurgeons? Or radiologists?
Yes.
I'm sorry? Radiographers, okay. So you're used to seeing images. Okay, that's really interesting to me to see that you guys kind of line up with their opinions. So that was part one, and of course there were tons more, panels for them to look at. I'm not going to put you through all of them because we'll be here all day. Then part two came, and what I did is I took all of the machine learned images that all three experts had said looked good. Right? So all the machine learning images that earned a score of 3, and I sent them to part 2, and I paired them next to their ground truth version. And I asked them, you see that there are errors between the machine learned image that you said was great, you guys loved it. And there's errors between that and now you see the ground truth version. Are the errors that you see acceptable to you? And they were able to revise their scoring of that machine learning image based on seeing the ground truth. So what I was trying to do here is I was trying to probe whether the machine learned images, they looked beautiful, yeah, they were great, but were they really being true to the biology and the pathology that exists in the real image? This is really important, because anytime you use a library of images to enhance a novel image, you're taking information from something that is not your particular case, and you're guessing, educated guess, right? But you're guessing at what these kind of patterns and noise ought to look like. You're never going to be perfect. It's not possible, right? So we have to know whether there are subtle differences in these enhanced images that could lead to errors. This is the question. And so here's a panel that they would see. So this was ground truth. There were some instructions that you guys didn't see ahead of time. I apologize. But basically, this is ground truth, and this is the enhanced image. Ground truth, the enhanced paired image. So you see the pattern there. So they were having to look like these two together and then these two together and try to see if the errors matter to them. What do you guys think? The top panel. What do you think about that comparison? And I know you guys can't quite see all the detail. I apologize for that. Sure. Do you guys think that the errors matter there?
It's just that the images are the same.
Yes. So this is the machine learning enhanced version, and this is the original CT image that it came from. So this is the ground truth image, and then this is the enhanced version that the surgeons already said, all three of them said, this is a good image, I'm going to use this. So I'm testing whether they really think that by showing them the ground truth version next to it. And you see that there are errors, right? So the brain comes around here, and it doesn't quite match the thickness here. The ventricles are a little bit enlarged. So what do you think? Would this matter? Do those look the same to you guys? They don't look the same, do they? What's that? Yeah. So can you think for hydrocephalus, can you think of what is the significance of the ventricles looking larger? Yeah.
It looks like it doesn't exist on the image of my right.
Yeah, you're right. You're right. You're talking about this right there, right?
Yes.
Yeah. Yeah, totally. So what could be the implication of that? Surgery speaking. Yeah. And again, I'm not a surgeon, so I'm just repeating what I've been told. What are your thoughts? Yeah. Yeah. So, for example, if you had a decent image to do your surgery, and then you ended up with this one, 6 months post-surgery, maybe you think you need to go revise the shunt because you're starting to build pressure on one side of the brain, when in fact you're not, right? So this is an error that I think, I hope now that we've spent so much time, I hope that the surgeons also said they didn't like that. Yeah, they did, good. So this is an error that can create a new surgery for this kid unnecessarily, right? So this is a risk. And keep in mind, there was a high amount of contrast loss originally in the image, a high amount of noise originally in the image. So, you know, the machine learning network did a really good job pulling out this detail, but it doesn't match enough to the ground truth, and actually it would alter the surgery path, which is what the physicians all said. And they all revised their score to a score of 0. So they said this image, in fact, was misleading. It is not an image we can use after seeing ground truth. So that's important. It does work sometimes. They all liked this one. They thought it matched the detail well enough for them. And they kept with the score. This had much less noise, but still quite a bit of contrast loss in the original case. So here's another just quick example. And in the interest of time, I'll just show you already what they said. So one of the surgeons didn't like this. So this went from being a 3 down to a number down to a 2. So it's kind of like uncertain whether it would be useful or not. And they ended up liking this one as well. So, and these actually had the same amount of contrast loss and the same amount of noise in the degraded version. So what I see from this qualitatively, we'll go to the quantitative stuff in here in just a second. But qualitatively, you can't necessarily depend on the amount of contrast or the amount of noise that you have in the image necessarily for the enhancement part. The biology, the physiology that's present in the image also matters in terms of the quality of the output of the machine. And maybe you could think of it as if there's some measure to tell you how similar what the brain that you're looking at is to the brains that you trained on. Maybe that has some effect, right? But I don't really know. I don't know if we've really teased that out yet. But it's enough to say certainly that it's not consistent completely, and that there's risk in using machine learning. So let's go back to the data from part 1. So this is just when life was simple, and we were just asking whether an image was useful or not, right? So what I did is I plotted. So this is for. Oh, I didn't put the resolution. I believe this is for the 128 by 128 resolution. So I plotted the data on the noise versus contrast reduction. And X's are data points that are bad, and the triangles are data points that were good, and the gray dots are kind of the uncertain, right? Where we had scores of 2 or 1. And it sort of matches up with what you might expect. You know, the less noise, less contrast reduction you have, the more good images you have, and then as you get further into the noise and the contrast reduction, you have bad images. And I guess I should also say, I didn't mention this before, but I chose which points to apply to the images completely random. So we of course didn't cover all points in space. Can't do that. But I used an algorithm to randomly choose the noise and the contrast for each resolution. And if you look at, so first what I did is I used a statistical method to try to define the boundaries here. I used something called logistic regression. And this is the dotted lines here. We're supposed to divide the data into what is useful and what is not useful. But then I started thinking, hey, that looks a lot like constant lines of contrast to noise ratio. And so I calculated the contrast to noise ratio for each point in space and superimposed these lines, and not really that brilliant, right? Because we're plotting contrast and noise, so of course the contrast to noise ratio is going to be important in this plot. But I noticed that it lined up pretty well with the statistical method that I used. So I thought I would reduce the space to not just noise and contrast, but just contrast to noise ratio, and perform another logistic regression. And that's what I ended up doing. And I showed, so this is the logistic regression, and without going into detail about the method, the way it works is you can use contrast to noise ratio sort of as a predictor. So how much contrast to noise ratio is in each image per resolution. So here we have 32, 64, 128, 512. And the method will give you this likelihood that an image will be useful based on the data from part 1 and the calculated contrast to noise ratio. And here you can see the raw data plotted on these lines, but up here is kind of what we like to look at. And this is interesting because what you see is, for example, if you have a 32 by 32 image, you need a lot more contrast to noise ratio in order to approach a useful image, the likelihood of a useful image, right? And then it sort of tailors off where a 512 by 512 image, you can stand a very small amount, a very low contrast to noise ratio, and still likely have a useful image. And, oh yeah, so let me pick this one out specifically and give some examples. So the pictures that you see correspond to the points on these lines. I tried to pick points that were, similar usefulness likelihood, but of course we don't have data points to cover every spot on this line, so I had to be a little sparing. But also interesting that I want to show you, if you'll accept this kind of stretch of the data, is if I were to plot the 3 Tesla and 3 Tesla and 50 millitesla MRI image with their contrast to noise ratio on this diagram. This was a 128 by 128 resolution image with the field of view of 25 centimeters, I think. Same field of view here, but 512 by 512. You can see that although the contrast to noise ratio is much higher here, the likelihood of this image being useful based on this data about hydrocephalus treatment planning is roughly the same, right? Both of these are likely to be useful based on the data. Now, the limitation here, of course, is that we did our study on CT images. But I don't think it's a huge stretch to say that the contrast to noise ratio between the two should yield marginally similar results. So this is an indication that from a $20,000 scanner versus a $3 million scanner for hydrocephalus treatment planning, we probably have the same diagnostic information. There are limitations here that are very important. In certain cases, you probably would not be able to get the exact same diagnostic information. So I'm certainly not saying this is proof positive, but it's an indication, right? It's interesting to think of it in this regard. So what about the part 2 data? Is the error acceptable? So the first thing that I did was I took the logistic regression curves from the part 1 data, and I calculated the contrast to noise ratio from the part 2 data and put it on those curves. And so down here, we have the contrast to noise ratio of the degraded images that went into the machine learning networks. Okay, does that make sense? So the bad images that we ended up enhancing all had really low contrast to noise ratio and really low usefulness likelihood. After the machine learning, their contrast to noise ratio all popped up significantly, and so did their usefulness likelihood. So the path from here to here with these data points is the machine learning. And we see that in the data. Almost all of the machine learned images were considered useful from part 1 information, right? But when you include part 2, where we go back and ask whether the errors were acceptable, we see this problem. And so what I have here is a table. This is the prediction. So based on the contrast to noise ratio alone, we predict that all of the 128 by 128 machine learned images will be considered useful by the surgeons. And close to 90% of the 64 by 64 images would be considered useful. Okay, so after part 1, the surgeons said that all of the 121 by 128 images were useful. They thought 97% of the 64 images were useful, and 0.03% were not useful of the machine learned images. So what we saw in part 1 actually matches the prediction of this logistic regression that we developed based on the degraded data, right? You guys following this? More or less? So when we get to part 2, this is where it gets interesting. Because part 2, they're asking if the errors are acceptable when comparing with ground truth, right? And now, with the revised scores of these enhanced images, only 25% of the 64 by 64 images remained useful, 39% of 128 by 128. We have this uncertain and misleading category here, where uncertain is some of the surgeons thought the image was no longer useful. Misleading is we changed from all of them thinking the image was useful to all of them thinking the image was not useful. So this accounts for nearly 70% of the data that we have that has gone on here. So clearly, the logistic regressions from part 1 don't apply to the enhanced images. So we developed a new logistic regression, which includes the usefulness likelihood of a degraded image. And on this axis, you can see the risk of misleading if you enhance the degraded image that you have for this site. So I'll take you through how that works. So if this is our image, this is our ground truth CT image, right? If I degrade this image to, say, a contrast to noise ratio of 1, so it's going to hit the curve right here, has a very low likelihood of being useful, right? And you can see that from the image. It's a very low image. Now, if I put it through the machine learning network, it looks really nice, right? Beautiful image. The CNR went to 8. So if we were just judging based on this axis, it's not even on the chart, right? 8 would be like over here. We would say 100% usefulness likelihood. But based on the part 2 data, we also know that we have the scale is not linear, so that the curves can look normal. But we know that we have more or less a 40% chance of actually misleading the surgeon if we use this image, based on how degraded it was in the beginning and the data that we have. So here we have this choice that we have to make. Do we use the enhanced image? Do we stick with the degraded image that we know is not useful? And our group thinks in this scenario, we definitely stick with the degraded image, because in this scenario, the responsibility and the assimilation of the information stays in the hands of the surgeon. If we give the surgeon this with no indication of risk, the surgeon no longer is in charge of his own surgery or her own surgery. So for this machine learning network that we used, we didn't find any scenario where you would have a low usefulness likelihood for the degraded image. And, sorry, did I say that right? Yeah. A low usefulness likelihood for the degraded image and low risk of using the image if enhanced. And so we prefer just having the degraded image and not enhancing at the end of this study. Now, we only tested one machine learning network. We had 80 images to train on. So this is not to say that we should all dump machine learning. I think there's a huge place for machine learning in all of the medicine that we're trying to do now and in processing. But it's an important risk to highlight. It's not a magic pill that we can put into our low quality stuff and end up with really high quality results. So I think it's very important to understand. So in conclusion, we do show that lower quality images can be useful in hydrocephalus treatment planning. I think this concept can be extended to many other necessary diagnostics. Deep learning enhancement carries a high risk of treatment-altering errors. Again, considering that we used a single deep learning network, there could be others that work better. But regardless, we need to develop new standards of image quality that focus on patient outcome rather than high-quality images. We need to know that we're getting what we pay for when it comes to these diagnostic technologies, and be sure that we're not outpricing ourselves. And so, of course, we have a very large team that worked on a lot of this stuff that we couldn't have done without, including collaborators at Cure Children's Hospital and here at Broward University. And then the money slide So yeah, last night we finished the magnet.
Does everybody have Google Colab now?
Yes.
Okay, great. So if you have, then go to that URL. It should start looking like this, called the GRE demo smart IPYNB stands for the Jupyter Notebook.
I didn't see that. I installed and you have to.
Yeah, so the link that's shared, there's a link that's shared on WhatsApp. There's a link that's there on WhatsApp.
Just see if it works. Yeah.
Oh, yeah, it should. Type C again. Yeah, I think.
These are very predictable.
Better.
Mine was actually stick. No, I see it. I was into.
You had a low resolution.
Yeah, that's right.
Yeah, I was about to change stuff, but this works still. You can have mine too. I'm going juice now.
Thanks.
Alright, so the first step that we're going to do is to install the programming library called PythonSeek. I will quickly show you. So this is the URL you want to go to. If you just search for PythonSeek GitHub, you will have the whole details more than what I can provide for now. This is the reference I can leave this with. I just saw that thing at the end of it if you think that's useful, but this has all of it, our publications, the other publications that use this work and so on. So it's got a whole bunch of details, but just for you to get going with that. Now the first step that we're going to do is to install this package. For those of you who know Python, this is by the PyPy installation called pip install. Please go ahead and hit that little triangle button. Say run anyway. You're not Google, but you're fine. There is going to be a runtime issue sometimes on this version of PythonSeek. You should see 1.3.1.post1. That should be the version that gets installed. Is everybody done running the first cell? It takes a while because it's going to download a bunch of packages and install it.
Come again with that.
All right. Is there anybody who has had trouble with that? Yeah, I think down the line this will give an error with the plotting. So we'll come back and restart the whole thing for sure. I think it's going to give us an error downstream. That's what I guess. Please go and import the library, which is Python sync, should run smooth. Similarly, math, NumPy, matplotlib will give you an error downstream. Looks like. Here's what I want to. So have you guys so far been exposed to field of view and MR imaging of some kind? Okay, great. So what we're doing here in this cell is just setting the sequence up in terms of, C is an object. I'm trying to say I'm going to set up a new sequence whose field of view is 256 mm. The matrix size is 256 by 256. Flip angle is 10 degrees. I want a 3 mm slice thickness, and my echo time is 4.3 milliseconds. My reflection time is 10 milliseconds. RF spoiling, which is basically a way of saying I don't want any residual magnetization, is 170. The last part is where it becomes super nice with this library. This system limits is for a Siemens 3 Tesla that we have, but once you get to know from Tom and Josh what system specifications are for your system, you can just go in and change it. So it design it for your system hardware specification. So right now we are running it for a 3 Tesla Siemens, but you could run it for whatever is the specification on your hardware down below. So go ahead and run that. So once you're done, let me know, it should just go through. In this next one, what you're trying to do is to say, I'll create a radio frequency pulse, a gradient pulse to do slice selection. This is essentially the events thing that I was talking to you guys about earlier, making some calculations on what should be the timing. So if you run that, you should be able to say, I'm going to play a 90-degree pulse or a 20-degree pulse or whatever the flip angle was, and then make some pulses on the gradient coil that you will see down below. You can, the ones that we are kind of winding around and around like an eye with an eye around the patch, that's the one that's the gradient coil. So you're controlling the current in the gradient coil by actually doing this bit of programming in here. The raster time is the number of samples you send to the gradient coil in unit time. In this case, it's 10 microseconds. So every 10 microseconds, you send a sample to the gradient coil and what it should be doing. The RF or the radio frequency coil gets an update of every 1 microsecond. This is the sequence itself, which is pretty straightforward. It basically says, in K-space, have they been introduced to the term K-space interface? Or maybe I can just quickly introduce them to that. Yeah. Okay. What you have to do in an MR scanner is, in a camera of a cell phone, when you click, you're getting the photons coming from the object falling on a CCD sensor. The number of photons tells you how bright or dark the image is. Of course, you can figure out also based on frequency filters whether it falls in the red wavelength or the green wavelength or the blue wavelength. So that's optical imaging. In MRI, we do things a little differently. What we do is we don't directly capture the photons from the object. It so happens that we end up capturing the Fourier transform of the object. Meaning, if there is a sine wave with 50 Hz and you captured that with an MR scanner, you're going to see a signal at 50 Hz in the data you acquired. So it's going to say, oh, there is a signal with 50 Hz. There might be another signal with 120 Hz. So for every such frequency, you get 1 point. Instead of the photons coming in, This is what frequency is in the object. You can imagine if there is something that's running very fast, you will get a high frequency information. If something's moving very slow, you will get a low frequency information. That's in time. You can have the same kind of motions in space as well. What this is trying to say is, I need a 2D grid, right? Like just you take a picture, you start the photons keep coming in, let's say in raster kind, like a dot matrix printer goes blip, 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 and then goes in the next row. Similarly, here also you need to cover 2 dimensions. The first one, let's say, is called the readout, which happens at 10 microseconds each. And then you step, you go to the next one, and then you acquire again. So for those of you who have any computer science kind of background, you can quickly think of it as 2 for loops. The first for loop is going in the same row. The second for loop is going in the column, right? So that's what this is doing. Ion range NY is basically the ion range NY is the number of phase inputs that goes column by column. Then length TE is essentially how many. This was meant to be for dual echo time, but 1 echo time, and then you go into the second for loop, which is actually here in this, where you acquire along the ADC. That means you're here. So let me take you step by step. You're on the first row, depends on how you would start. Let's say you're on the first row, and then you wanted some magnetization, you wanted to get the signal. Whenever you say RF, you're transmitting something, and then you got the signal in this step, and then you're opening your receive and listening to it. So that's what it is. So you transmit and you receive. It's more like an antenna. On the antenna, you're pulsing something, you're waiting for some time, and trying to hear back. That's it. That's all you're doing in an MR scanner. Along with the antenna, you also need these gradients that spatially encode. So the line that I've highlighted is the second for loop that runs along the row. The one at the top is the one where you keep stepping through, and you fill a 2D grid. So that's that. You will be able to visualize. Okay, here I think you will hit an error. I think this is probably one of the first things that we could have got. Okay, so you did see the error, and the way to fix this error is to do what our friend here suggested: restart the runtime. And then run through those things. You should be able to get through that error because matplotlib essentially was complaining. And once this runs, I'll tell you how this works. There we go. So let me. This is probably useful. So here's what's happening. This is your antenna, the RF coil that you're going to see downstairs. This is basically saying send a signal on that RF pulse. The way you do it is by sending a current with a frequency that is decided by the magnetic field strength, so you can be resonant. Once you send that, wait for some time, and then send the current to another coil called the gradient coil. Have it for some time in the opposite direction, and during this period, you get what is known as the echo, and that's it. So that's the receive or the ADC. Let me explain this with a simple analogy of a sonar with a ship, right? Let's say this is the sonar sending out the signal, this part, and then this part is to basically say, within that vast amount of ocean, just look at a particular place. That's what that gradient does. And after some time, you hear the echo coming back from the ocean floor. And that's this. So you transmit You do a bunch of things with the gradients, and then you hear the echo coming back through the ADC, which is analog to digital converter. That's all there is. And then once you've done that, remember we were at the top line, now we have to go to the next line. The way you go to the next line is by incrementing or going one step up in that other dimension. That's the second line. The third one is to select a part of the body which is called slice selection. But that's pretty much it. With this you can figure out, you can change, the order of these events, the shape of these pulses, based on your understanding of MR physics downstream. When you play the virtual tabletop, you should be tabletop games. You should be able to identify what should I do to the sequence to make different things happen on the hardware down. So this is like controlling the hardware using this Google Colab. Now, how do I? Okay, how do I use this and put it on the hardware? We can run the last cell, which will essentially download the file. Oh, here. Let's change the date. 22, today is the 27th, right? 09. Okay, there we go. And then you download the file, say Allah. You should be able to take this file, go, and if you have the Marcos spectrometer attached to your scanner below, you should be able to run this on that. That's it. I'm happy to take questions on why we chose those values, how were those values decided, why we did what we did with the other two gradients and all of that. But if you have gotten to this point, you just had your first pulse sequence program downloaded, and then you can start from here. How many of you had trouble downloading the file?
Yeah, I am not seeing that.
Did you get the timing? How many of you got the timing diagram? Like with the different pulses? How many of you were able to see? Oh, good, just one. Timing diagram done. Okay, good. So I'll come around and I'll try to debug. Oh yeah, on with this. Yeah, you can do it. Yeah, you can do. But now the problem is you can run through all of these again. Okay. Yeah, it's just a matter of kind of run around this. You got the timing. Then my team was because we had a ESM meeting on. That's when this comes to this. It's just that I'm right with the 60% downloading that was
Some of them like that because they face
Sorry, I did have this error that I fixed. These two file names should match. Otherwise, you'll be writing one file name and downloading something else. So, if that matches, then it should be good. Is there anybody who needs help in downloading the same file? We can open up the same file.
I think it is so you refer the text.
So when you guys are done downloading and open it up, I just go through and tell you what it means. Yeah. Oh, just WordPad. They say open it. It should be the Notepad or WordPad. Any of those. You can open this file. If you are how many of you are on a Windows system here? On a Windows operating system? Okay, so you can open this with either rich text format or Notepad or WordPad or even Microsoft Word. So it could be any of those word processing softwares.
Is this duration of every
No. 3 milliseconds will be the RF pulse.
That's what I'm.
Yeah.
Do you
The raster time is resistive. In the system. No, that's that would be resistance.
yeah.
So when you go to system, you have this student and there are defaults within the apps, pp.ops. So you can print system and then you can see all the.
Oh, okay.
It's a default. It's a default option. Because we know that the system works at microseconds. That is 100 kilohertz acquisition packet. So we know that, so we don't.
Yeah.
But each of these could be a different way to go to length. But it's one clock.
Yeah. Okay.
Yeah. So the slicing, like I said, for RF, you can convert it to 1 microsecond.
Yeah.
Shrinking is usually you can push. On the GE system, you can push it to 4. Now, when you go back and you have 6 and GE,
I've never seen
so the defaults here will work perfectly fine. Yeah.
It's one important bit. Is what the.
Oh, slicing. Yeah. So each block would be a variable length design. And depending upon which event, meaning the delay, RF, any of the delays, ADC, which is a readout, external is for triggering like cardiac triggers, right?
Yeah. I think knows already that an ADC 2 takes some or
oh yeah. So
9.
So the first block.
Yeah.
So yeah, I will go through. The first block has an RF and a GC for size-7. Yeah. The second block is essentially has GX and GY, mostly reminders. Yeah. The third block is a delay so that you can get to the echo time that you want. Yeah. And fourth is going to be the readout gradient and the ADC. So that's pretty much what we are. It rolls out, you can see the same pattern repeating. Those are different, for different basic codes. If you scroll to the bottom, you'll see when you say RF1, that means play RF of shape 1 time. Yeah. 1 is defined down below, could be a sync pulse. So it will define a compressed version of the sync. So that's the block, event, and shape. Alright, so has everybody been able to download their first pulse sequence program zip file? Yes, we downloaded it. Open it with Notepad or WordPad or Microsoft Word. It should open. So I'll just tell you what this is doing again very quickly so that you can connect to the hardware that you guys are putting downstairs. It has the following different lines going out, right? The D stands for delay, meaning telling your hardware do nothing. Then the next one is RF, telling your radio frequency coil, saying I'm going to play out a shape or a pulse on that coil. GX, GY, GC are the 3 gradients that spatially and selectively excite whatever samples you want to excite. ADC is on the way in to collect the data from the system, and external is if you need some external triggering, like ECG trigger or respiratory trigger, things like that. What you're asking the hardware to do in the first, so the block number is the first block in time. You can match this with the timing diagram that you see on your Google Colab page. The first block will have an RF played out along with GZ. You can check that. If you look at the first things that happen, there's the RF and GZ to selectively excite a slant or a slice. Then you have GX and GY coming next in time. Then you have a delay, meaning nothing is happening, and then you have the readout and the readout gradient and the ADC. So this is telling you what is happening in time. It's like watching a movie as you go from the top to bottom. If you scroll below, when you say RF play 1 or RF play 2, it will tell you the shape. So, yeah, sequence of shapes. So, shape ID 1 has this shape. If you plot this on an oscilloscope or print it out, it will be a compressed version of a sync shape, which is a sine pi by pi. But this is essentially the way the software communicates to the hardware. This file is giving instructions particularly to the hardware and saying, this is what I want you to play. At this time, this is the kind of shape I want you to play, and then there is a bunch of hardware in there that will actually take these instructions from the computer and play it on the real coil. So that's where we got. You could take this with the right tools. You could play this on a Siemens or a GE or a Bruker or any system with the Marcos spectrometer, even the CROSPA. The KR2 spectrometer, so you should be able to play all of these sequences. But what I think is also equally relevant, if not more, is if you guys can punch in that URL on your web page, right? Can you go to that if the URL is visible? I just read out github.com/imr-framework/vs-table.com. I'll let you guys try to install maybe offline today or tomorrow. Otherwise, I can have a specific session just helping you set up, because the setup on this is not as straightforward as the Google Colab. There is how do you want to do it, you can do it. But I will help you set up. I want you to just experience how this works out. Again, this is based on your challenge, so we've been working on it since 2019. I'll just show you the games. Yeah, so this is how it looked once you run that. It basically lets you play games so you can get introduced to MR. Again, with the Piper seek, you need to know a little bit of what a full sequence is, how to play a pipe, how to play a full sequence, and all of that. With this, you don't need to know anything. You can start from zero and then build your way up. Kev has done a fantastic job of this, of course. Let's play some games. It's about climbing up Mount Presidents. You earn 3 stars to unlock the next one, and then you get 5 stars if you want to get a prize, and then solve some puzzles and have fun. So I'm going to log in here. So here's an example. I'm not going to play this whole thing, and it's not even something that you can see in the. So you get the instructions on the left hand side, and then you should be able to see the rest. My image display is so bad that I can't see anything. But you could increase the field of view. And you return to the native resolution. Yeah, you could, or you could use the admin account as well. But you need to kind of compile to get there. But now that you can see there are a bunch of instructions, you follow the instructions and then you play the game. And as you get closer and closer, you answer these questions and then you go. You should be also able to learn as you play with something like this. When you click on it, it gives you, I know it's not legible there, but once you click, you'll be able to know what this is about. What's the field of view? What does matrix size mean? What does voxel size mean? What does zero fill matrix mean? So each of this is defined, and if you need more details as well, I think you have some help that you can go and get on this. But this is a nice way for you guys to get started on this. There are some cool. Yeah, this is about weighting. This is probably the most important, especially if you're radiographers and you want to play with this. You can start changing these times and then start looking at different contrasts. Clearly, there was a proton density kind of thing. So you can start playing with this and start synthesizing different contrasts and understand what MR works. Again, you have a bunch of exercises, but you do have help that you can use to understand each one of these, and you also have quiz questions to take it. There are some really cool animations. If you want to, I think game 4, press play. So this is probably the coolest if you're looking at NMR physics. It kind of gives you where the magnetization is. You can look at how the magnetic field strength works at different magnetic field strengths. You have different magnitudes you can see, and then you can also have the RF. So you can say what kind of 90-degree pulse, where is my magnetization going to end up? this is a real nice way for people to learn pulse sequencing and understand how to go about. And again, you don't need to know everything because most of it is defined here, and it gives you a bunch of instructions and questions to go about. You also have projections. You can play with different kinds of projections and start. So you can load different models, see what the projection is, what the 1D projection is, and so on. Yeah, there are a couple of other games that Java has implemented in this, but I will see image flow, but those four basic games on the left hand side should get you started and be able to understand acquisition and reconstruction with it. So I would recommend this as a good starting step before getting into the Bible sequence. Yeah.
How do I get to that?
You have to install it. Yeah, you have to install it, and that's the installation instructions.
Yeah, I think we're looking at
No, if you type virtual scanner, VS tabletop. If you Google for VS tabletop GitHub, so give you a bunch of different ways to start.
That's that part.
Sorry, and that URL up there that I did allow. Yeah, so that should give you the installation instructions. I will, one of these days, if you guys find it interesting and want to install this on your laptop, I will spend some time on a Windows system first, get it to work, and then repeat those steps to you so you can also install maybe tomorrow or after tomorrow. But I think this is a good way of getting started with anyone with no background, slowly working through the exercises with instructions in there, and like Gerva says, get to the top of Mount results. Alright, I'll stop my initial demo, but I will come back and whenever there is time available, we'll install virtual scanner tabletop games on your system as well. Because how many of you know how to create a virtual environment? Okay, so we will do that. It should be about 30 minutes of install, but once you set up, then you should be able to do this pretty much. You don't need internet connection for this once you've installed it. It's on a browser, but you don't need internet connection. You could do this at home, or you'll be setting up a server on your own laptop. I'll help you set up the server if you find this interesting. So I will leave you with this website. This is where they put out all the intelligent development framework. So we have our projects here. There are different projects. The virtual scanner is here. I don't think the virtual scanner tabletop is here. I will share these URLs with you guys so that you have access to all of these. And then you can look at a whole bunch of repositories that we have for open source. So I'll share these links with all of you so you can look at any or all of these for things that you want to play. But I would highly recommend the tabletop to get started, virtual scanner games, and then that will give you a good bearing on all these things, and you can do it at your own pace.
Show you the results that we've got, what we've learned, and why I'm also particularly interested in low field MR just a little bit at the end. Right, so HAV is short for HIV-associated neurocognitive disorders. So HIV, we lived in what they call the cart era, where everybody that has HIV, hopefully, or most people with HIV, will receive proper treatment. And HIV dementia is almost not being spoken of at all. Back in the day, before people got HIV treatment, a big percentage of people actually developed a dementia that resembles Parkinson's disease. I don't know if you're familiar with it, but it's a disease that affects your way, your ability to think, your ability to move, and also makes you depressed in and of itself. And you move slower, and you get, some people develop tremors like they have in Parkinson's. But that largely disappeared, but it didn't disappear completely. So that meant that we needed to re-look at HIV. Does HIV, because now what happened is people don't develop severe dementia, but they develop minor neurocognitive impairment, which means people would forget their keys, they would be discoordinated, they move slightly slower, which might be able to interfere with complex tasks, such as driving and so on. So we needed to understand, and this is way back when, in the 2010s, we need to understand, does HIV still infect the brain even though we give treatment? Even though we take out all the HIV out of the brain, does it still somehow affect your brain? And if so, how does it do this? And also, does drug therapy, the cart itself, also play a role? Because we know some of the medication we give people actually have side effects, brain neurocognitive side effects. In other words, it gives them nightmares, it also makes them depressed, and also affects their nerves. So we also want to know, does the drugs themselves also not maybe play a role? So how did we plan to do this? We wanted to use functional neuroimaging because it is not invasive and it can tell us something about how the brain functions. Now, how do we use MRI to tell how brain function works? Now, firstly, we need high-field MRI, at least currently. We use that, but also we take advantage of a property of the brain, that the brain is actually a very lazy organ. It only sends blood to the specific parts that it's using currently. So if you're looking at a flashing checkerboard or a flashing light, the blood increases in the back of your brain, your occipital lobe, where you see with. When you move your hands, the blood moves towards your motor cortex mostly. And this allows us to study specific parts of the brain. This is also referred to as the bold curve that was discovered. It's a well understood curve of how when you stress out parts of the brain, when you make parts of the brain run, the blood flow actually increases in a reasonably predictable fashion. So this allows us to model for this. But how do we do this? Well, first we push someone into the MR scanner and we give them a little periscope. We give them a little periscope so that they can see a very large projector at the back. And we can give them instructions, very well-timed instructions in the back. And we also usually give them a button to push so that they can give us feedback, that we know that they're actually following the instructions that we do. So a good example of it is what we call a tapping task, a motor task. So we ask them, you're lying in the scanner, it's dark, and you see instructions in the scanner that says move your hand. And you're lying there and you move your hand in a very specific way. And then we give you a slide for 30 seconds. For 30 seconds we ask you to move your hand. And then for 30 seconds we ask you to look at the little star. Then you're not moving your hand. And we repeat this process on and off for 30 seconds on, 30 seconds off. And then ultimately we can run a linear model across all the voxels in your brain, all the regions that we scan, and then we can see which parts of your brain fit best. Where does the blood flow stay low and for 30 seconds, and then go high for 30 seconds, low and high, and we can match this pattern as we scan rapidly brains every 1.6 seconds. So that's the other part here, is that why I feel is that we can scan the entire brain so that we can look across the entire brain and see where does the blood flow go and where does it follow the pattern or the task that we're trying to do. And then, so this is a result of the task I just explained. It showed that the regions, when you take the entire brain that we scan and match this model across the whole brain, only specific regions have been more likely to be active than others, according to our generative linear model. And then we can see here, you'll have to believe me if your neuroanatomy is a bit hazy, is that we can see that the motor cortex is activated, parts of the basal ganglia, and also the cerebellum on the opposite side. So we had this is one of the first studies we did just to see, does this technique actually, everybody does it overseas, but does it actually work for us? You know? So, and we can see that we can actually get a reasonably accurate signal. But of course, we're not interested in tapping tasks. We're interested in HIV and how it affects complex processes. So now how do we do that? So for that, we need to use tasks that involve certain parts of your brain that potentially could affect you in ways that are responsible for your motivation and how you move and act during days. These regions that we suspected HIV is actually impacting. So to understand how the tasks work, I need to tell you guys a little bit more about what our understanding is of how brain function works these days. And it's very high level things, don't quote me on this, it's just a conceptual understanding. So here's the brain, and I've highlighted very, very broadly the frontal lobe, or the prefrontal lobe, and the striatum, which is in the middle of the brain, the deep gray matter. That's the striatum is blue here, and the frontal cortex is red. We think these regions we call the frontal striatal system. We think that this is involved for most of what makes us human. So I don't know if you guys know, or clinical guys might know about Phineas Gage. It's a guy in the 1800s where he worked with on a railway track, and a big railway sleeper actually went right through his brain, right through his frontal lobe, and it lobotomized most of his removed most of his brain. But he was still able to move, he's still able to talk, still able to do a lot of things. You ask him to do things, especially early on when his brain was still not compensating for loss of most of his frontal lobe. He wasn't able to do things on his own. People had to tell him what to do. So we think the frontal lobe is responsible for a lot of the parts that make us do complex behavior. And that most of neuropsychiatry is actually seated in this region. But what we've learned in the last couple of years, especially with fMRI, is that it's particularly important that these two regions communicate with each other, the striatal and the frontal parts, that they talk with one another. So we need to know what both of them are doing in a given task. So how do they work? So a conceptual way of thinking about this is that the striatum, the blue parts, is like the manager. And the cortex is more like the people he manages. Let's say he's thousands of people that he manages, or the student body, and this might be the big professor, the striatum. So the brain, the frontal lobe, has very rapidly fast-acting neural circuits, billions upon billions of neurons that fire all the time. They never actually quiet down. The striatum, however, it's more on a slower path. Every couple of seconds or milliseconds, it does something. And through animal work, they've discovered that the striatum modulates what happens in the frontal cortex. So it doesn't micromanage people, but it does encourage certain regions to work harder, and sometimes, and other regions it says, okay, you guys can relax now. Or it says, something is happening, all of these people need to be active now. Early on, that's why it's so hard to see if the striatum is actually damaged, like the dementia processes that happen over a large time, because if your manager disappears, your students and everyone are still going to do the job, but it's over a while, those people are going to break down, they're going to start Facebooking, Instagramming, TikToking, and then slowly things break down. So that's why we think it's important that these two communicate with each other. If you lose your frontal lobe, if all your students are gone, nothing's going to happen. The manager's still going to sit there, right? That's what happened to the Phineas Gage example. But the dementia example is more the opposite, where we think that the subcortical region is damaged, and then it's more subtle and it's harder to see what's actually going on, because the manager is just there now and again. So he's not really motivating the students as they should be motivated. So they're doing their job, but not so great. So the regions, we are interested in a sub-region of the frontal striatal system called the ventral frontal striatal system. Sorry, I'm skipping a slide here. The lower parts of this region. So it's just a subset of this larger network. And what does this region do? It's important in motivating you. It takes you away from what you don't like, and it takes you to the things that you really love. So, and this is classically abnormal in drug abuse and impulse control disorders. People who gamble and those things happen, they can't stop gambling because they can't figure out that what they're doing is not resulting in good things. This is also a part why moving, why it's much better before you get the car, you're more excited than you're actually getting the car, because you have the basal part of the brain that anticipates things. The manager anticipates, oh, this car is going to be so amazing, you're going to love it, and then everybody has to just think of how they're going to use this car. But when you get the car, all the students and the brain is just, yeah, okay, this is not so big, and it's red, and there's a new model out, complex things are happening now. So that's partly how the motivational system works. But we think that this was particularly, we thought this was abnormal in HIV, because HIV people suffered a lot with apathy. They couldn't get going, or they were impulsive, or they got depressed. So there was something abnormal in their motivational structures, reward system of their brain. Okay, now this is all good and well, but how do we actually test this? And this is actually one of the more fun tasks, because it involves actually giving people money. And it's also hard to believe that this actually works quantitatively, that we can measure it. So it's quite a nice thing to do. So what we do inside the scanner is, we first show them a face, and then we show them a star, and then we show them a target. We tell them as well, whenever you see the target, you must press the button as fast as you possibly can. Never deviate from this. Press it as fast as you humanly possibly can. And then sometimes that face is going to smile, and sometimes it's going to smile, and sometimes it's not going to smile. When it smiles, we're going to give you money if you press the button on target. If it doesn't smile, we're not going to give you any money, but you must still press it as fast as you can. Right. So now you can actually put in an experimental condition, a behavioral experimental condition. We also didn't tell people how they should behave. We just told them they must press the button as quickly as possible. So what do you think would then happen? If your brain is told you're going to get money, you're going to press that button faster, right? So the manager parts of your brain is going to excite it and tell your other parts, hey, this is money, press faster, you know? And then the neutral part, it's not going to happen. You're going to press it a little bit slower, relax, you know, I'm not getting paid for this, whatever, you know? So we can, and then afterwards, we give a feedback screen. We give it to you green if you pressed it correctly on target, and we show you how the money is going up if you did it properly, and we give you a red screen if you missed the target. So, what happens in this task? You have a period of anticipation where you see and remember we are comparing, we have a general linear model, so we have to compare one condition with another. We want to see that the average signal is increasing from a base. So in the boring, not getting money, we want to see this signal increase from boring to exciting. We want to see parts of the brain get more excited when we promise you money. And that happens more in this section over here, in the reward anticipation phase, we call it. The feedback phase is when the students get the car, when they got the money, is then your other part, your complex part of your brain deciding, was this worth my effort? Why is this so important? Because you don't waste all your time getting excited like kids do. Kids have very different functional characteristics, but it's important for the brain to decide when to invest all of its energy. Right, so, and then we have a functional hypothesis, as it works. It's also based on animal studies, that the manager striatum regions will get more active when we anticipate things, when we promise you something, and orbital frontal cortex, that's its associated prefrontal region, will then get more excited when you actually evaluate the reward. Right, so when we did this, we actually got very good results. It was people with very little education. It was in our people and people that were the people with the most HIV, and they got it right first time. And we got very good results. We could show that the regions that we want to activate properly does get activated. And so we can use this as an experimental task to study motivational control in HIV. In other words, we can compare people that are early HIV without any drugs, aren't depressed, and no cranial effects. We can have them do this task, compare it to people, controls that come from the same community who would react in the same way to the task. So then we can see, do these brain regions actually differ in terms of their function? So now we've got the task. Right, and I'm just going a little step back. This is our findings that we got over the course of many years. Is the first thing we did was, we wanted to see, even before we chose the task, we wanted to see, does fMRI itself actually measure something? Where in the brain does HIV actually impact? So we wanted to also see, okay, we've got a nice task, it's validated, but does it activate the regions we want it to activate? This is with a meta-analysis that we did on all fMRI studies that was conducted before, I think it's 2011 or something, 2013. And we showed here that fMRI showed that the HIV virus does actually consistently impact your frontal striatal system, especially early on in the illness, before you have even any cognitive things that you can measure with pen and paper tests. It showed that there was an impact. So now we have a broad strokes. It could show us we've got the right task. We can study it now. But the other thing that we were interested in as well is its neighbor or its cousin, Parkinson's disease. What happens when we do this reward task in Parkinson's disease? Because this dementia is very similar to HIV. If you remember, I said early on in HIV that people saw that these two are similar. We want to also compare what happens in these two illnesses. So we saw in Parkinson's, where we start off with just healthy volunteers. I think this was students, and we promised them money, and we wanted to see what happens. So here in this graph, we show when the face doesn't smile, when you're not promised money, and this is when you promised money. And this shows that there is a significant increase from the neutral condition to the rewarded condition. So it shows that we could successfully excite students reliably, and we replicate this task. But then we tried older people, people that have problems in their striatum. Well, not problems, but let's just say as you get older, your striatum relaxes. I said a lot of worried faces here. This is to say that your striatum, as you get older, you know, children are a little bit insane, right? Let's just get that between you and me. Their brains are very different from older people. As you grow older, your striatum relaxes a bit because, you know, the cortex got this. I don't need to do this so much. I don't need to invest so much energy and time to decide what to do. So your dopamine relaxes a bit, your subcortical regions relaxes a bit. And we could show this effect on fMRI. There are older controls Maps with the Parkinson's also did this. But so this is an example of healthy aging. Let's call it that. You relax. It's not like you don't lose control. But the problem is in Parkinson's disease, we showed that there's a flat line, that there's no increase between neutral or reward. So you can't decide now what's good, what should I chase after, or what should I just leave alone. So you're just either doing nothing, you're apathetic, or you're impulsive, you just do any and everything. That's why Parkinson's has a lot of apathy and depression and low motivation. So we largely showed this and we replicated it in another study as well. But then when we did it in HIV, we also got similar results. Through this. We had our control, so control conditions showed that they had healthy anticipation, but we showed abnormalities in the subcortical regions of the brain, that there is an element of function loss in HIV just before early HIV, before they got onto medication. We also showed in another task that's a bit more complicated as well, that the same region is also affected. So it's a complicated motor task. We also showed that the subcortical region is more affected, the blue parts, than the red parts, than the cortex itself, especially early on in the infection. We believe that's not because the virus is so clever, it's just because the virus pools around these regions early on in infection in the CSF spaces, and then it starts chewing away at these subcortical regions and only spreads later on to the more general brain. We also showed that this is related to brain atrophy. So the more your function declines in the subcortical region, the more your brain shrinks, your frontal lobe shrinks. That's why they saw a lot of frontal lobe atrophy, subtle atrophy that you can only need the segmentation algorithms to pick up. So that was the story. So we discovered that, well, we confirmed that it's a frontal striatal process early on in infection. In fact, it has a predilection to the blue regions, subcortical regions. And we also showed that it is kind of relevant because it also affects your brain downstream, so that things start to atrophy as well. But now the clinical questions come up. What can we do about this? And how relevant is this? How important is this? Because remember, they might have this decrease in function, but it might not actually generalize into much. So it might not have a strong impact on them. And some people more vulnerable than others. So we started firstly looking at genetics. This is with the German team that we looked at. We saw that a certain gene is very overexpressed in HIV. So a lot of people would have this gene, and this in both the German sample and the South African sample. And this gene is actually specifically important for the function of your blue striatal region. It's a dopaminergic gene, so it's very important for this region. So we didn't have the money, so we had to do this in Parkinson's because the funders were more interested in Parkinson's. We haven't done this in HIV yet, but we did show that this gene is associated with worse function. When you have this gene, you're a little bit worse than when you don't have this gene. This was, there are of course a lot of problems with this kind of research. There's a lot of genes that code for the same thing. This is also like very close. If you repeat this measure as well, there's a lot of issues, statistical issues as well. There's a lot of noise in this, so we have to be careful with this interpretation. It's not necessarily the gene that's doing it, but the downstream effects of having this gene. But it's still a good start. We also showed on that we couldn't find any other genes associated with dopamine also that has the same effects. But it was still a start to show that there is a connection between your genetics, how your brain functions, and that some people might have strong functional brains, others might not. So that's why some might develop dementia in HIV and others don't. But it's still very early work. Last thing I want to show you guys is the impact that we had in children on ARV drugs. Because if you remember, I mentioned that there's some drugs that affect the brain neurocognitively. So when you take this drug, you get nightmares, and you get some people get peripheral neuropathies, and I know that their nerves get impacted and that kind of thing. So now, of course, we're worried not just for the adults, does this impact their brains? Adults' brains are strong, so they can take a lot of punishment, so it's not necessarily going to have permanent effects for you. The problem is, though, if kids use this, and kids do, because a lot of children have HIV, and now we're wondering, does this, are you particularly vulnerable to the effects of this drug when you develop? So we did one of our fMRI tasks, and unfortunately we did see that the children on efavirenz, this is on and off efavirenz, both have HIV. The children off on efavirenz had quite a strong effect. They responded much slower to our prompts, so they weren't as quickly to make a decision. And their brains, also the cortical regions, were also affected in a certain way. There was had lower activation and lower function. We did, although we published this, but subsequently we did see that we did an analysis, and when we followed these kids up, they didn't have that largely vanished. They didn't seem to compensate. But the importance here is that we can see this and we can monitor this with fMRI, and we should be very judicial in what medication we prescribe, especially to developing children, because we never know where the brains are going to end up. So the good news is there is a new drug called Dr. that actually replaces efavirenz. Slowly we will be replacing this, and also we don't think this will have any permanent impact on the children, but still it's important that we do keep an eye on this. The neurodevelopment is one of the important places for us to go further. And so the last thing is just our future directions. So we've now actually looked in adults, and this is a Dutch HIV sample that we collaborated on, showed that the effects of changing from efavirenz, the drug that showed to have harm, that we think is harming people, switching to an alternative drug, we showed that they have some improvement in their cognition, that they're doing better on IQ-like tests, but also showed that that is associated with having stronger function in their cortex as well. Actually, I think it's in the blue subcortical regions. But we're still submitting this paper, so that's still going on. But the last thing, though, is although I showed you all of this, very excited, this took years to do all of this study, and it's very slow, it's very expensive. We could only scan a small amount of people with a high field. So that's why we're particularly interested in looking at brain age estimates in HIV. HIV does seem to age your brain faster, because of its not resemblance only to Parkinson's, which is an aging thing, but also because HIV affects your, seems to damage your immune system, and that's not very great for your brain. So you age faster. So there's a lot of people that have shown how HIV affects the age estimation. So we use algorithms to look at brain age to kind of guess what's your brain age from a MR scan. There is some work there shows there is a difference. But the thing now is, of course, if MR, I feel it's very expensive. So that's why I'm here as well, to look at low field applications and how we can scan more people and get more information. Particularly for things that affect our local populations. Right, thank you. That's it.